Okay, so ready to dive into black holes. We're digging into that 2020 Nobel Prize in Physics, and you guys sent some seriously cool sources over.
By the time we're done with this deep dive, you'll be able to drop some serious knowledge about not just how we know black holes exist, but the evidence for one super close to home.
Our own galactic black hole neighbor. Now that's a story. But gotta back up a sec, the sources all said. Like, really understanding what a black hole is key, yeah.
Totally. Imagine, like, taking the entire Earth and squeezing it down to a pea.
Whoa.
That density. That's what we're dealing with. Now, picture the sun crammed into, say, the size of downtown Stockholm. You start to get a sense of that crazy gravity.
It's wild. Something so dense light can't even get out. Almost hard to believe. But our sources said the idea of black holes, it's way older than we could even prove they were real.
It's true. Way back in the late 1700s, Jean Michel, Pierre-Simon Laplace, they're theorizing about dark stars, so massive lights trapped.
They basically predicted them without the tech to back it up.
Yeah.
That's some next-level science imagination right there. But then Einstein rolls in with general relativity, and that changes everything, right?
Exactly. Einstein's the one who showed us gravity's not just a force, it's warped space and time. Think of, picture a bowling ball on a trampoline.
Okay, yeah.
It makes a dip, right? Anything with mass, like, say, a marble rolls by, it'll curve towards the bowling ball because of that warp. Now, swap the bowling ball for a star, trampoline for space-time, marble for anything with mass planets, light. That's general relativity in a nutshell.
So we're all warping space-time. Mind blown. But here's the kicker. Einstein, with this huge theory, he actually doubted black holes were really a thing.
He did. Even Einstein thought, like, come on, too bizarre. But then 1965, Roger Penrose comes along.
Oh, this is where it gets good.
Right. With some seriously intense math, he proves that if matter gets dense enough, remember, Earth is a pea, black hole formation. It's unavoidable, baked right into general relativity.
So he proved Einstein right that they were possible, but wrong for not believing they were out there.
That's huge. What'd that do to the science world at the time?
It was an earthquake. Suddenly we had the math to actually understand these things that were like stuck in sci-fi before. That's what got him half the 2020 Nobel Prize in Physics.
And rightfully so. But finding something invisible, that's going to be tough. No light escaping? How do you even start looking for a black hole?
That's where our other Nobel winners come in, Reinhard Genzel and Andrea Ghez. They tackled that impossible-seeming problem finding evidence of black hole. And they did it using gravity itself.
Speaking of incredible discoveries, let's talk about the black hole in our own galactic backyard. You mentioned Genzel and Ghez found evidence for it. What can you tell me about Sagittarius A?
Genzel and Ghez, they each led separate teams, right? And for decades, they studied the center of our Milky Way.
That's dedicated. You know, observing the galactic center, it's like trying to see through like a really thick fog. It's tough. And that's where infrared telescopes are key. Lets you peer through those clouds of dust and gas.
Like cosmic X-ray vision.
Exactly. Both Genzel and Ghez use this tech to track how stars move near the center of the Milky Way.
Okay, I'm picturing two teams, super powerful telescopes, steering into the cosmic fog. What did they find lurking in there?
What they found, it like redefined what we know about the Milky Way. They both saw stars moving around some invisible object at crazy speeds, whipping around, and the only explanation for that much gravity, a supermassive black hole.
A supermassive black hole in our galaxy. That's amazing.
That alone is huge, but what's truly mind-blowing is this thing's mass 4 million times the mass of the sun.
4 million suns, all crammed into one point in space. I can't even imagine.
And almost beyond comprehension, right? But here's what's wilder. It's all packed into a region smaller than our solar system.
Like smaller than our solar system. How can something be so massive but so incredibly tiny?
That's the thing about black holes. They push our understanding of physics to the absolute limit. It's this extreme density, this warping of space-time that creates that incredible pull nothing, not even light, can escape from.
So Genzel and Ghez basically weighed an invisible object by watching stars dance around it. That's some next-level cosmic detective work.
Right. By analyzing how fast those stars were moving, their trajectories, they figured out the mass of that invisible dance partner, Sagittarius A, the supermassive black hole at the heart of our galaxy. And that work, that's what got them the other half of the 2020 Nobel Prize in Physics.
It's amazing how far we've come in understanding these celestial objects, from theories about dark stars to proving their existence and now finding one in our own cosmic backyard. But I have a feeling we're just scratching the surface when it comes to black holes. There's still so much we don't know, right?
Oh, absolutely. The more we learn about black holes, the more we realize how much more there is to discover.
Yeah.
These objects are constantly challenging our understanding of the universe, raising profound questions about, the nature of reality itself.
Well, I am hooked. We've covered the basics of black holes, delved into the work of these incredible Nobel laureates, and now I'm ready to dive into those unanswered questions. What are some of the mysteries scientists are grappling with today?
Get ready, because we're going to journey into the unknown. We're going to explore the mind-bending possibilities of what happens inside a black hole, unravel the enigma of their formation, and uncover the cutting-edge research that's pushing the boundaries of our knowledge. It's funny to think about black holes. They get this rep for being like destructive monsters, but they're actually key to how the universe looks today.
Oh, interesting. So more than just cosmic vacuum cleaners. But if nothing can escape, how do they even affect anything outside that event horizon?
That's where things get really wild. Remember we were talking about quasars earlier, those super bright, outshining whole galaxies kind of thing?
Oh, right. From way earlier, the beacons we can see billions of light years away. I'm still wrapping my head around how anything, let alone something as dense as a black hole, makes something that bright.
It's all about this process, accretion. Think of it like a cosmic whirlpool gas dust all spiraling down towards the black hole. Gets heated up millions, billions of degrees, just blasting out energy.
So it's like a superheated cosmic spotlight.
Mm.
But how does that energy escape, if even light's trapped once you cross the event horizon?
Key point. The accretion disk itself, it's outside that point of no return. Like a balancing act, matter gets closer and closer but doesn't quite fall in. And that swirling stuff, it gets so bright we see it across the universe.
So the insane energy from quasars, it's not from the black hole, but right outside it, in that disk.
Exactly. And here's the even cooler part, quasars. That's just one way black holes mess with their surroundings. Did you know they can actually launch jets of matter at almost the speed of light?
Wait, seriously? Like, superpowered cosmic fire hose is coming out of a black hole. Sounds like a sci-fi movie.
Sounds crazy, but it's totally real. These jets, some are thousands of light years long, and they're powered by that same energy source as quasars, the accretion disk.
But how do you launch anything that fast? From something so strong, nothing escapes. What's the mechanism even?
It's this whole interplay of forces, gravity, obviously, but also crazy strong magnetic fields, and the black hole's own spin.
Hold on, black holes spin. I always picture them like static points in space, just sitting there.
Oh, they definitely spin, and not just a casual spin. We're talking speeds close to the speed of light. See, as matter falls in, especially if it's already spiraling, it transfers some of its angular momentum, makes the black hole spin even faster.
So it's like a figure skater pulling their arms in. The black hole pulls in matter, spins faster and faster.
That's it. And that spin energy is immense. Now picture magnetic fields, like threads, going through the black hole and its disk. As the black hole spins, those fields get twisted, wound up tight. It's like a cosmic nozzle forms.
So you're saying this cosmic nozzle focuses the energy from the disk and boom, you've got these jets shooting out. A cosmic particle accelerator powered by a spinning black hole.
That's a great way to put it. It's a spectacular display of the power of these things. But it's not all just pretty lights either. These jets can seriously mess with the galaxies they're in.
Really? Tell me more about how those jets shape a whole galaxy. It's wild to think something born from so much gravity affects things on such a huge scale.
Those jets, they're not just light beams. It's highly energetic particles that travel insane distances. They can bump start star formation, heat up the gas between stars, even change the whole shape of a galaxy by controlling where stars can and can't form.
It's like those black holes are tending their own galaxy gardens, pruning some areas, encouraging growth in others.
It's this balancing act, destruction and creation. Black holes can be destructive, but they also kickstart growth and evolution on a galactic scale.
This is blowing my mind. Seems like every answer just leads to more questions.
Well,
But before we go too far down that rabbit hole, we've talked about stellar mass black holes, the supermassive ones. But is there anything in between?
Now that's a question that takes us to one of the most intriguing puzzles in astrophysics, the mystery of intermediate mass black holes.
Intermediate mass black holes. So Not the babies, not the supermassive giants, something in between. That's like the missing link.
Right, like finding that missing piece of the black hole family tree. We've got a good handle on stellar mass black holes, those leftover bits from massive stars going supernova. Those are like your standard size. And then, of course, you've got the supermassive ones hanging out at the centers of galaxies, millions, billions of times heavier than our sun.
Yeah, those are the ones that really grab the headlines. But it is fascinating to think there might be this whole other category in between. Where do these intermediate mass black holes fit into the picture?
That's the million-dollar question. Astronomers think they might hold the key to understanding how those supermassive black holes even form in the first place. Think of those stellar mass black holes as seeds. The intermediate mass ones could be those seeds, growing, gaining mass on their way to becoming the supermassive behemoths we've been talking about.
So like the teenage growth spurt phase of a black hole. Are they as hard to find as teenagers are to get to clean their rooms?
They're definitely elusive, but we have clues. Astronomers have spotted these insanely bright X-ray sources in nearby galaxies. The energy coming from these things suggests something way bigger than a stellar mass black hole, but not quite at the supermassive level.
So we're searching for those telltale signs, those energetic bursts that might point to these intermediate black holes hiding in plain sight.
Exactly. And the search is leading to some really exciting avenues of research. Scientists are using all sorts of techniques, not just X-ray observations, but gravitational wave astronomy too. We're talking about catching the ripples in space-time caused by these objects colliding. It's cutting-edge stuff.
That is absolutely incredible. It just goes to show the more we uncover about the universe, the more we realize we don't know. It's kind of humbling, isn't it?
Absolutely keeps you grounded, that's for sure. We've come a long way from those early theories about dark stars, but it does seem like every answer we find just leads to more questions. But that's what makes it so exciting, right?
You said it's a journey, not a destination. So as we wrap up our deep dive into the world of black holes, is there one key takeaway you want our listeners to walk away with today?
I think the biggest thing to remember is that black holes, despite their reputation as these cosmic monsters, they're not just fascinating objects of study. They are absolutely essential to how the universe works. They influence the evolution of galaxies, the birth of stars, maybe even the very fabric of space and time itself.
So more than just holes in space, they're engines of change, shaping the universe as we know it. That's pretty awe-inspiring when you think about it.
It really is. And the more we understand about black holes, the more we understand about the origins of everything around us, even ourselves. It's all connected.
It's been an amazing journey. Thanks for being our guide today. And to all our listeners, thank you for joining us on this deep dive into the fascinating world of black holes. Until next time, keep asking questions, keep looking up at the stars, and never lose that sense of wonder.